covalent bonding, and we've done the properties of the compounds containing these bonds. Now, the metallic bond is a new one. You've done ionic bonding and covalent bonding previously. Now, the metallic bond is just very simply, we say we have positive atomic rests, means the nucleus is positive. The electrons around it, something happens to the outer shell electrons. We say they become delocalized. It's as if those outer shell electrons don't know to which atom they belong. So we talk about a positive atomic rest because if a metal loses its outer shell electrons, it becomes positive. Okay, so the definition of a metallic bond, we have a metal lattice of positive ions. Why positive ions? Because the outer shell escape. Okay, and they can go to any nucleus that they want to. All right, so if you want to get a picture of it, if I filled a flask with marbles, the marbles would represent the positive atomic rest, and if I added water to it, I can slosh the water around. Okay, so these electrons are free to move. They aren't held around in the last shell, in the outer shell. Okay, now, we say the Coulomb forces, charges, Coulomb forces, all right, between the negatively charged electrons, the delocalized ones, okay, attract the positively charged ions, the metal ions. Why do we have ions? They've lost their outer shell electrons. No, those electrons, it's like they don't belong to anybody. They can just go where they like. So Coulomb forces are weak or strong? Strong. Coulomb forces are strong. So strong forces holding these positive ions together. The negative electrons that can move, they hold those positive charges together. This is a piece of metal that's bonded, yes. And that's just sodium. I've just put these two examples on because sodium only has one outer shell electron. So each sodium will lose one electron that becomes delocalized. All right? Yes, zinc has got 2 electrons. If you had to guess, which one would be the better conductor? I'd say zinc, because it's got extra electrons that can move. Okay, and the more electrons there are that can move, the better it can conduct, if it was perfectly pure. Okay, but remember, there's electrostatic forces between positives and negatives. This is a piece of zinc. No, this is a piece of zinc. That is what it looks like. Okay, that is the bond. All right, the attractive force between the positives and the negatives. So we say the electrostatic forces between the positive and negatively charged particles are strong. In other words, what do we know about the melting and boiling points of metals? Usually fairly high. Why are they fairly high? The forces holding the particles together are strong. Why are they dense? The forces pull them together. All right. So, melting and boiling points of metals, sodium loses 1 electron, while magnesium loses 2, and aluminium will lose 3. Aluminium will have stronger electrostatic forces than what magnesium or sodium would have. Who would have the highest melting and boiling point? Aluminium. Because a +3, -3 charge is going to hold stronger than a +1, -1. You follow? All right. Must be logical. So the aluminium will have stronger electrostatic forces. So aluminium as a pure metal will have a much higher melting and boiling point than the other two. Will have a higher melting and boiling point than sodium, which is only +1 and -1. Magnesium would be in between because it's +2, -2. Do you follow? Okay. Then, the properties of metals. What are the properties of metals? Shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. Okay, and now we can actually add something else. Usually, high melting and boiling point. Usually, high density. Why usually? First 2 groups. Okay, the first 2 groups, those metals are less dense. Sodium and potassium float on water. So that doesn't fit the pattern. So, if I ask you a question, give me properties of the metals that lie in group 1 and 2 that differ from the properties of the transition metals. Do you tell me shiny, malleable, ductile, sonorous? No. You tell me low densities, soft metals, low melting and boiling points. Do you understand? If I ask you metallic properties of the transition metals, specifically the transition metals, you're going to tell me shiny, malleable, ductile, sonorous. No, you're going to tell me they usually have high melting and boiling points and high densities. Do you understand? Okay, if I ask in general, what are the properties of metals, then you start with shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. Well, if you want to go further and differentiate between group 1 and 2 metals and the transition metals, you can. But usually you can just look at the marks, one fact per mark. Okay. So let's go and have a look at the properties of metals just in general at this point. They are shiny. Why are metals shiny? Well, they have delocalized electrons, and these electrons can move between the positive atomic rests, which means that the electrons on the surface can reflect light, and anything that reflects light is shiny. Okay. Malleable and ductile. Another word for malleable and ductile is they are workable. Now, why are they workable? I want to go back to the pictures of the bonds. Now, if I hit a block of zinc with a hammer, bang, I'm disrupting the crystal lattice, aren't I? Now, if it was a normal ionic bond, where the bonds were rigid between positive and negatives, I would shatter that crystal, wouldn't I? But why does this not shatter? Because no matter where I push the positive atomic rests, what can the electrons do? They can move in between, and they maintain the attractive forces. All right? That is why metals are malleable. You can hammer them as much as you like. The electrons move in between, maintaining the attractive forces. They are ductile, meaning I can pull them into threads. All right? How does that happen? Well, we find, because it's an orderly arrangement. If you imagine a stack of marbles that could form a block, the layers of the positive atomic rests, can you see that they can slide in relation to each other? All right? So what happens is, when it's ductile, we pull it into threads, which means we are pulling these layers off each other. Why does it not break apart? The electrons are delocalized, they can move, and positive and negative attract. All right, so they maintain the attractive force. If you keep on pulling, somewhere at the point it will break, yes, a piece of steel by pulling. Because you have to break a chemical bond. No, does it make sense? Okay, so malleable and ductile, also because the positive atomic rests, there we go, can occur in layers, and they are held together by these forces, but the forces holding them are not rigid. What does rigid mean? It's held in a fixed position. But if the positive atomic rests, the forces between them are not rigid, it allows for movement. Okay. So the positive atomic rests can slide over each other without breaking apart. Remember, positive and negative will attract, always. The delocalized electrons maintain the attraction because they sort of are pulled together with the positive atomic rests, because the negative is attracted by the positive. Sonorous. Normal words, makes a ringing sound when it's struck. Why does this ringing sound, ping, travel through the metal? Well, very simply, it's a vibration, it's energy, and it is because the electrons can travel through the metal. They take the energy with them. And that is why we get that ringing sound that is very characteristic of metals. A piece of wood doesn't make a ringing sound. When you hit it with a hammer, it goes tuck. But if I take a metal, the bell hanging in the courtyard there, if you hit it with a hammer, it goes dong. All right. That is sonorous, and it's sonorous because the electrons, the delocalized electrons, can carry the vibration through the metal, so it lasts for a longer period of time. Good conductors of electricity? Well, current is moving charge. So electricity is connected to charges that are able to move. Which charges can move? The electrons. And in metals, we find the electrons are delocalized. So if I put a potential difference across the edges, they go from a point of high potential to a point of low potential. So why are metals good conductors of electricity? Well, conduction actually implies particles gain energy, they vibrate. The one bumps into the other, so it causes the next one to vibrate, and that one bumps into the next one, and it causes the next particle to vibrate. So, except for the normal vibration and transfer of one particle onto another, they bump, and it transfers the energy like that. That's conduction. We also have the fact that these electrons are free to carry charge through the metal. So another substance could be a good conductor, but metal is a better conductor because except for the positive atomic rests that can bump and transfer the energy, we have electrons that are delocalized and free to move and carry that energy. So good conductors of electricity, the delocalized electrons are free to move. Good conductors of heat, just said the metal ions are closely packed, they're close together, metals are dense, so it's just very easy to bump into the one next to you and make that one bump and the next one bump and the next one bump. Because we have an ionic lattice and the ions will bump into each other, transferring the energy from one particle to another, one positive atomic rest to the other, and the delocalized electrons can also take energy and go, usually from a point where there's lots of energy spreading to a point where there is less. We have to have a look at the last unit of topic 2, which is balancing of equations. We've done balancing of equations as we've worked with the chemical reactions from grade 8, grade 9, grade 10. Now we are just going to formally go through the basics of it. And then I've got a worksheet for you. All right, so when we write chemical equations, we must always keep in mind that matter is actually a form of energy. And just like we cannot create or destroy energy, we cannot create or destroy matter. All right, so on the left-hand side, we always have the reagents, and on the right-hand side, we always have the products. Okay? The arrow tells me the reaction goes from left to right. Sometimes when we have reversible reactions, we will use an arrow that looks like that. It means the reaction can go to that side, or it can go back. Okay, but we will have a look at specifically the reversible reactions at a later stage. Now, I'm going to put an example up on the board. For example, hydrogen plus oxygen will give me water. Now, when we write a chemical equation, the first thing is you have to have the correct formula. You have to know which elements are diatomic and which are not. And then you must know how to work out the formula, for example, of water. We know hydrogen's got one bonding place, oxygen's got two, so we need 2 hydrogens and 1 oxygen. Now, the next step would be to balance the equation, because if you look at it like this, then we will have 2 oxygens, but we've only got 1 oxygen, and you can't have 1 oxygen floating around. It doesn't work that way. So you need to get this equation balanced in such a way that everything on the left-hand side must equal everything on the right-hand side. So we go 2 hydrogens, 2 hydrogens. That seems to be okay. 2 oxygens, but here we only have 1. So I need to have large numbers in front of the elements or compounds. So now I have 2 oxygens, but what happens to the hydrogens? They become 4. So I need to have 2 hydrogens. All right. I can draw it as follows. I have a hydrogen, and I've got oxygen, okay, and I have got H2O. I've got oxygen, a hydrogen, and oxygen, and hydrogen. All right. Okay, now, if we go and look at what happens during this reaction, in the first place, any reaction requires some energy to start with. If there is enough energy in the environment, the reaction will occur spontaneously. For example, if I take sodium and I throw it into water, there's so much energy from the environment, the reaction wants to occur, and it goes. All right? Other times, for example, like this piece of wood the desk is made from, if I wanted to start burning, I have to hold a match under it for a while, put a piece of blitz for a couple of minutes, and then I can take it away. Once it's burning, it's going to keep on burning. All right? So the first energy that you need to put into the reaction goes into breaking bonds between the stuff that are going to be your reagents. So bond breaking occurs on this side. Now on that side of the reaction, we find that bond making occurs. In other words, the oxygen reacts with, 2 hydrogens. All right? And here, this oxygen, reacts with those 2 hydrogens. Can you see we get the formation of 2 water molecules? You all follow me. Now, when chemical bonds are made, in other words, bond making, it gives off energy. So this one takes energy, and this one off energy. I must calibrate the board. All right. Now, we all know a chemical reaction is either exothermic or endothermic. When will the reaction be exothermic? When more energy is given off during bond making than what was used during bond breaking. And if it's an endothermic reaction, then we require more energy to break the bonds than we require, or that we get from bond making. Do you follow? Okay. So that's just on the bonding. If we go and have a look at this, we can see now the elements or the atoms of the elements or compounds on the left-hand side is equal to that on the right-hand side. Now we also indicate so-called state symbols, all right? And that is just very simply a small letter S in brackets after the element or compound for solid, small letter L for liquid, small letter G for gas, and then when we have substances that are dissolved in water, we refer to them as being aqueous. All right. So, if we write some chemical reactions, I'm going to do 1 or 2 examples. Let's say we have got aluminium reacts with oxygen and it forms aluminium oxide. The formula? Yes, Al2O3. Oxygen has 2 bonding places. Aluminium has 3 bonding places. Aluminium stays as it is. Oxygen is diatomic, so it's O2. Put in the state symbols. How do we know aluminium is a solid? It's one of the metals, and we know on the periodic table how many elements are liquids? 2, mercury and bromine. Which ones are gases? Hydrogen, nitrogen, oxygen, fluorine, chlorine, plus the noble gases which don't react anyway. So there are 5 gases that you need to remember. The rest are all solids. Yeah. So aluminium is a solid. What do we know about oxygen? Colorless, odorless, tasteless gas. So there, we've got gas. And aluminium oxide, how would you know what state that is going to be in? It's a salt. What do we know about salts? Hard, brittle solids. You understand? So aluminium oxide is a solid. All right, we're not working in a more watery medium, so there's nothing that can be aqueous. Now we start balancing. Balancing large numbers in front. They usually say balance the following equation, include state symbols. Okay. So we have 1 aluminium there, but here we have 2. So we need probably 2 aluminiums. Over here we've got 2 oxygens, but there we've got 3. Now this is a difficult one to balance because to go from 2 to 3, you must multiply with 1 1/2. But you can't have half an element. How would I get rid of the half mathematically? There's a trick that works 90% of the time. If that one is 2 and that one is 3, then I will need 2 there and 3 there. That's just a trick. It doesn't always work. Let's have a look at something like nitric acid plus calcium carbonate. We are going to get calcium nitrate. Like that, we are going to get CO2 and we are going to get water. All right. Now we have to start balancing. You simply start counting, starting at one place, going to the other. Just have a look before we start counting. Can you see that this nitrate part, this polyatomic ion, hasn't broken up? It stays as a nitrate, so you balance it as a whole. We can already see, okay, 1 hydrogen, 2 hydrogens. So we will need to put a 2 in front of it. So how many nitrates have I got? 2 nitrates. There I've got 2 nitrates because they are in brackets. So I have 2 of this whole thing in brackets. How many calciums? 1. 1. How many carbons? 1. 3 oxygens, 2, 3 oxygens. Let's put in state symbols. What do I know about nitric acid? Solid, liquid, or gas? It's a liquid. Okay. For the acid, you can put, not all acids are liquids. No, some are gases, but then the hydrochloric acid, for example, is a gas, but it's dissolved in water. Okay. So this acid, you can write it's a liquid or it's aqueous, because sometimes it is a gas dissolved in water. Sometimes it's a solid. For example, things like citric acid is a solid, and I can dissolve it into water. All right. So that one would be either liquid or aqueous. Then calcium carbonate, it's a salt. So solid, liquid, or gas? Solid. Has to be a solid. Okay, now calcium nitrate. This is a salt, but we are working in a watery medium. Now, something very useful to remember, and we'll have a look at solubilities a little bit later on, but all nitrates, anything that's bonded onto a nitrate is soluble. So this thing is not going to be a solid, but it's going to be AQ. All right, that one is a gas, and that one is going to be a liquid. Depends on at what temperature the reaction occurs, but this one, with the acid, we don't usually work above boiling point. I'm going to do one more, and then I'm going to give you a worksheet. One more reaction. Let's take phosphoric acid plus calcium metal is going to give me calcium phosphate plus metal plus an acid, hydrogen, yes, good. Okay, what's this thing's formula going to be? How many bonding places does calcium have? 2. And phosphate? 3. So I need 3 calciums and 2 phosphates. All right, state symbols. I'll go AQ, or liquid. Solid, it's a metal. This thing is going to be AQ, and that thing is a gas. All right. Let's balance. How many hydrogens? 3. How many hydrogens? What's the trick? Probably. Do you agree with me? Just swap them around. Now, how many phosphates have we got? 2. How many phosphates have we got? Seems to be okay. How many calciums? And there. So I need 3 over there. Fixed up. Right.
Win free airtime with One Africa TV. Share your comments on the channel. SMS your feedback, name and town to 555. One Africa TV. It just gets better.
Grade 10s. We have to have a look at Unit 8, Ionic or Electrovalent bonds. The word electrovalent is just a new term they use. It refers to the bonds are formed as a result of electrons. Okay, so the word valency, which they sort of have avoided up until now, refers to bonding places. And electro, because it involves electrons. Okay, so the bonds are formed with electrons. All right, atoms combine to bond with other atoms to become more stable. That's the only reason for forming a chemical bond. If I go and make a compound that is unstable, it doesn't really help because it's going to naturally react and break down to something more stable. So when elements in nature react with other elements to form, they form more stable compounds. For example, the iron in the ground is mined as the iron or iron oxide or iron sulfide because it's more stable than the pure iron. Okay. And it happens when the outer shells are filled, whichever method they use, with electrons. Now we can fill the outer shells by one of two methods. We can lose or gain electrons. You were taught last year the metals tend to throw away their outer shell electrons and form positive ions, while the non-metals tend to gain electrons to fill up their outer shells, all right, forming negative ions. Or by means of the covalent bond, where the elements overlap their outer shells and they share outer shell electrons. And we will have a look at those bonds as we carry on. All right, the term cation and anion. Anions are negative ions and cations are positive ions. What is an ion? An atom with a charge. How do atoms get charges? Losing or gaining electrons. If they lose electrons, what charge do they get? Positive. If they gain electrons, what charge do they get? Who does not understand that? Have a look at that when we do the ion. Okay, atoms lose electrons, forming positive ions. What is a positive ion called? A cation. So it forms a cation. Metal atoms lose outer shell electrons. Okay, so they form positive. Forming a positive ion. Atoms lose electrons. Okay, metal atoms lose, forming positive ions. I thought I had a mistake. It is the cation. All right, in general, people, remember the periodic table is divided between metals and non-metals, metals below the step. In general, all the metals lose their outer shell electrons. Metals become positive ions. All the non-metals, with the exception of hydrogen, become negative ions. Hydrogen works as if it, or behaves as if it is a metal. That is why it sort of belongs to group 1. Yes, it's got something to do with that. If we have a cathode will attract cations. And an anode will attract anions. Okay, so the anode is positive, it attracts anions which are negatives. And the cathode is negative, so it attracts cations which are positive. You mustn't confuse them. All right. Okay, so here we just have some examples of cations. All right. The opposite then of a cation is an anion. And anions are atoms that have gained electrons, so they have a negative charge. Cations and anions. Non-metal elements in general gain electrons, forming negative ions. For example, chloride, oxide, nitride. People remember how it works? Group 1 elements have one outer shell electron. Are they going to lose one or gain 7? Lose one. It's easier. So they get a +1 charge. Group 2 elements have 2 outer shell electrons. Is it easier to gain 6 or to lose 2? It loses 2. Group 3 elements have 3. Are they going to gain 5 or lose 3? Lose 3. It's logical. Group 4 elements. Gain 4 or lose 4? Lose or gain, just have a look where the step goes. What are they going to do? They are going to lose. What are they going to do? Gain. Because non-metals gain electrons and metals lose. All right. The group, where do we go? 5 elements. Lose 5 electrons or gain 3? It's going to gain 3, so it's going to become negative. Group 6 elements. Lose 6 or gain 2? It's going to gain 2. It's just easier. Okay. Group 7 elements. Gain 1. Okay, so you understand that, no? All right. Okay. Now we have to have a look at the Bohr structures. Now, we've done this in grade 8. The Bohr structures, we represent the nucleus of an element. Let's say I want to do the Bohr structure for carbon. We usually write the symbol of the element, and then we have the shells, and we have to mark the electrons in the shells using dots or crosses. Carbon has got 6 electrons. We should know at this point the first 2 electrons will go into the first shell because it's got place for 2 electrons, and the next shell will fill up until it's got 8. There are only 6 electrons altogether, so 1, 2, 3, 4, 5, 6. That is the Bohr structure for carbon. Yeah? Yes? Yes, you did. Yes? Yes, it's the same. All right. Now, the nucleus for carbon, we can say it has got 6 protons to indicate that it is carbon. All right. So there's nothing new from that. Here we have Bohr structure showing how sodium will lose its outer shell electron. When it has lost this electron, okay, remember the whole atom overall gains a positive charge. You don't always have to put it into brackets. We usually just draw it over here with a positive charge. All right. An anion, in other words, the atom must gain 2 electrons because it must form a negative ion. So here we have simply 1, 2, 3, 4, 5, 6, 7, 8 electrons, 2 in the first shell, 6 in the second shell. It's got place for 2 electrons, and we find that the 2 electrons go in there, and the overall charge on that ion is 2 minus, because it has gained 2 electrons. They differentiate it. They want you to do it behind it. And then when you write, if you want to say calcium, you go +2. Okay, gains an electron, it's negative. Remember, if something has got 5 protons, it's got 5 electrons, then it will be neutral, because each proton has an electron. But if it gains 1 electron, then we have 5 protons, but we have 6 electrons, so 5 will cancel each other out. You're left with 1, which is minus. You understand? So when you gain electrons, the charge becomes negative. When you lose electrons, the charge becomes positive. All right, here we've had a look at it. Group 1 elements all lose 1 electron, forming +1. Group 2 will lose 2, forming +2 ions, etc. Okay. Take note, when we go to the non-metals, they gain electrons. So over here, these are non-metals, and those are, and remember we said well, some are going to lose and some are going to gain. The metals will lose, the non-metals will gain. Now, hydrogen behaves like a metal. It loses one electron. Hydrogen is the only exception that you will work with in terms of group 1 elements. Are all metals, they become +1. Hydrogen's not a metal, but it loses an outer shell electron. Yes, it'll behave like a metal in a bond when you want to make, for example, a salt. Well, no, it doesn't always behave like a metal. Hydrogen chloride is covalent. Now, naming of atoms and ions, people, we've done this before. It's not difficult. Remember, when we name a compound, if a compound consists of, let me say, magnesium and oxygen, we don't call it magnesium oxygen. We call it magnesium, and we change the second one to IDE, magnesium oxide. All right. Normally, we write the metal part first. Otherwise, if it's something that contains hydrogen, we write the hydrogen first, but not always, because methane, for example, is a different one. And ammonia. All right, then we write the hydrogen second, but in our acids, the hydrogen comes first. But as we do them, you'll get used to them. So the name ends with IDE. All right, hydrogen sulfide, aluminium chloride, etc. Then we get some compounds. And when we look at the polyatomic ions, then some of these compounds, they end in the word letters ATE or ITE. If we look at something like H2S, H2SO3, H2SO4. Okay, how do we differentiate with a name? That first one is just straightforward. This is hydrogen sulfide, IDE. All right? Now, hydrogen SO3, the SO3 is the polyatomic ion, and we'll do them a little bit. It's the sulfite, ITE ion. So this would be hydrogen sulfite. Okay, so it's ITE. And that one is sulfate. It's going to end ATE. All right, so we will have hydrogen ATE for sulfate. All right. There we have two examples. There's aluminium nitrate. All right. And there we have sodium sulfite. So you have to be a little bit wake up. All right. But we will do the polyatomic ion still. So then we'll have a look at those names. Then the formation of ionic compounds. What is an ionic bond? Can you remember? Metal bonding onto a non-metal. What does the metal do? Loses its electrons. What does the non-metal do? Gains electrons. We have a positive ion and we have a negative ion, and they attract. All right. Coulomb forces are strong electrostatic forces. All right. So in an ionic bond, we actually have a transfer of electrons from the metal, because they lose it, to the non-metal, because the non-metal gains the electrons. Those electrons can't go up into the air or into solution. They must go from one substance to another. All right. The moment the metal loses electrons, it becomes positive. The moment the non-metal gains the electrons, it becomes negative. We have electrostatic attraction between opposite charges. So then electrostatic attraction, oppositely charged particles hold the ions together in a crystal lattice. What's a crystal lattice? Orderly arrangement of particles in a solid state. No? All right. Now, the lattice structure of sodium chloride. Sodium chloride is actually very interesting. Sodium chloride has a formula NaCl. So for every single sodium, there is one chlorine ion, or chloride ion. Now, when it forms a crystal has a very unique shape. We can use the shape of the crystal to help us identify what salt we have. Because the table salt crystal will differ from a copper sulfate crystal. All right. Now, if you could build a sodium chloride particle or crystal apart, we will find there are thousands of sodiums and thousands of chloride ions. In one sodium chloride crystal, I can have a big crystal or I can have a small crystal. The formula stays the same. It gives me the ratio of the metal ions to the non-metal ions. Now, in sodium chloride, we find, which one is bigger, sodium or chlorine? We find in a crystal of sodium chloride, and now must look very carefully because this has been cut, so it's difficult to see. If I look at that atom or ion, can you see it's bonded onto 1, 2, 3, 4, no, there must be more. Okay, this is very difficult to show you. 1, 2, 3, 4, 5, and there would be 1 as well, 6. Just have a look at this. It's difficult to draw because it's a flat surface and it's a three-dimensional structure. But in sodium chloride, each sodium ion is surrounded by 6 chloride ions in 3 dimensions. Okay? And each chloride ion on its turn is surrounded by 6 sodium ions. So the interaction of those charges must be very strong, holding it together. Sodium chloride has a very high melting and boiling point because the forces holding the particles together are very strong. Okay, will you remember that? 6 chloride ions surrounding 6 sodium ions and 6 sodiums around each chloride. And it forms a cubic structure. You don't need to know the...
I like rhinos. I like them very much. Future here in this area is depending on the tourism. The future generation, they can see and they can benefit from their own resources. Animals like rhinos, elephants, the big five, you benefit from them and it must be respected. You are not feeding the rhinos, you are not giving them order, so it's a free business. I take 2 of my sons, which was little bit 5 years old. They were young guys, so they asked me questions. Why are we here? Why are we sleeping here? I told them this is our resources and this is our future. My first memory of going with my dad is that I learned new things. As I grow up as a man, I see an opportunity in it. So I decided to look for a job pertaining to tourism. So that's when I was employed at Palembang. So I decided to go for tour guide studies, because I grew up with the tourism industry, the wildlife, the rhinos and everything, to bring that experience to the tourist. You can see the hyena. The biggest changes, I was employed, getting paid, and also I can now support my family.
It's a cultural thing. It's coming a long way. Even if you go to area like Treverfontein, area was a lot of paintings. You will see rhino engravings on the rocks. That is an indication that the interaction between human, especially the local communities, and wildlife is dating back. That intimacy relationship is coming for a long time.
We are right here now at Palembang, and Palembang is one of the big lodges in the heart of the desert. And as you can see there is Jumbo standing behind me, which shows it's really a tourist area. We do have elephants, lions, but as you can see, the desert is the heart of the rhinos. This is the main breeding area of the rhinos, is what we found here in this desert.
It's the largest free-roaming population of black rhinos that you find outside national parks in the world. It's a population that communities in the northwest have taken responsibility themselves in managing this population with the structures that government has put in place, more specifically the establishment of conservancies.
These people, before independence, they took it upon themselves and decided that wildlife is our heritage, and through history we've been living with wildlife. And having wildlife in your area is like having a garden.
Because of all these animals, we've got the communities that benefit from all this wildlife, and it's like a triangle that fits into each other. And the communities looked after the wildlife doing their own thing, and the communities benefit.
So already there were this intergenerational relationship between mankind and wildlife, and that bond is what our people actually wanted to see it continuing.
Very few countries have the wildlife that Namibia has. What is also important is the policies that Namibia has put in place, which also involves communities to be engaged in the management of the wildlife species and also to benefit from the wildlife resources.
Turn conservation into a rural economy, turn conservation into endless opportunities that would actually cater for those young people that have nothing else to do.
If it was not for rhino economy and tourism in this area, it was really difficult for young people to get or find a job.
We are conservation engineers. We make conservation work in an unfenced area, and through that, we want to turn the wildlife into the rural economy that will benefit the rural communities.
So we can see now wildlife is doing very well, the lodges are doing well, and the community is also benefiting. So it takes all three together.
Devastating hit over coronavirus fears. Airline industry is facing its biggest threat to travel since 9/11.
Since March, when COVID-19 hit Namibia, things actually become very difficult. In the first place, all the lodges closed down because of COVID-19. With us, say the Rhino Trust, we had some donors cutting on their funding. And then we had, in the same time, a poaching case of 2 rhinos that was poached. We had less boots on the ground, and poachers could actually see. Now it's our change to go in and do something. So COVID-19 was tough on all of us. Ginger Morning, who is one of our trustees, actually came up with the idea of, why don't we ask you to go to buy some gold for us and make gold bars, and then we sell them for rhino conservation.
I was fortunate enough to have a chance to have lunch with Clive Johnson, the CEO of B2Gold in Vancouver, Canada. And I looked at Clive and I said, you know, we've got rhinos, you've got gold, let's do something. Let's create a coin or a medallion or a bar using your resource to create a sustainable source of funding for rhino conservation for the future.
There was it. The gold was bought, the bars was made, and I think it was 31st of January that we launched the bars in Windhoek. And suddenly one morning I had an email from my office, from my finance person, saying, these people don't have salaries. So I said, oh, what now? So I picked up my phone and I phoned Mark Daw. I said, Mark, I've got this problem. He said, but we've got a fund already ready for you. You just have to apply, put a proposal in.
1,000 ounces of gold can make an enormous difference to the livelihoods of the communities that live up there. We are, in essence, providing income and providing a livelihood to the communities. In the absence of tourism, especially now with COVID-19, even prior to that, when we had such a bad drought, the communities became even more dependent on the natural economy.
The idea is to make this a fund that will last for the next 25, 30 years, or even longer. And a portion of that will be distributed immediately as needed. And in this case, the COVID-19 crisis necessitated us to distribute funds to pay salaries to help people in the field.
The proceeds of the sales from the gold bars will be going towards responsible NGOs. And we've identified Save the Rhino Trust as the key NGO. And IRDNC, one of the first organizations that was in the Northwest, integrated rural development and nature conservation, so that ultimately the funds go to the communities and various aspects of their war on poaching.
To be able to support those hardworking men and women that are always in the front line between the poachers and the rhinos.
If it was not for B2Gold and the golden bars, I think by now we should have been in big trouble.
By extracting the gold, you reinvest it in other renewable resources.
The gold that's coming out from the ground is actually protecting the wildlife that's working on the ground, which is a very good symbol for the others.
I wish this was my bar. This is the 500 gram gold bar. So you'll see on this side you've got the Etiendeka Mountains and you've got the mother rhino with her calf. And then on the reverse side, we've got the serial number, you've got the Rand refinery stamp, which is very important. Anywhere in the world, people will recognize the stamp and they will know that this bar contains 99.99% gold.
It is gorgeous.
We wanted to make a biggest contribution. And at Ballowwood, we see that as a way of giving back to the community.
Okay, so there you'll see the 500 gram bar.
Very special.
Feel the weight. It's incredible.
This opportunity which presented itself is absolutely a once-in-a-lifetime opportunity.
We're privileged to have this.
This is just absolutely gorgeous, and I think this showcase really what the project is all about.
It's from 24 karat Namibian gold.
I'm looking at these rhinos is put there like Miss World photogenic, I would say.
There are only 1,000 of these gold bars, rhino gold bars, in circulation.
As far as I'm aware, it's the largest single donation of any corporate to the conservation of biodiversity anywhere in Africa.
Therefore, we so much appreciate and would want to continue as a government to work with B2Gold.
And the fact that it's happening here in Namibia is something that we can all be extremely proud about and very grateful to B2Gold.
Thanks to having this literal pot of gold through the funding for the Rhino Gold Bar, we're able to step in now and make sure that those trackers are supported, and so are their families and their communities.
We make sure that people sustain their jobs going forward. And who doesn't want gold?
And the B2 Gold Rhino Gold Bar has come in at a really critical time now, particularly with tourism being closed off and those forms of revenue not coming in.
To say we have the biggest rhino population or black rhino population in the world, let it be for the rest of our lives. And it's that heritage that we have. It's our resource that we can all look after and protect.
It's our heritage. And it's also good that other people like B2 Gold are also seeing it that way.
It's actually a very nice link between the investor that buys this gold bar, the rhino tracker in the northwest of Namibia, and the black rhinos. It's an intergenerational thing. The rhino trackers teach their children how to track rhinos, their children get taught, and so it flows down.
This is something that I want my children to have, and that we leave a little bit of a B2 Gold legacy. And if I can be part of that as part of my family, I'd be very proud.
It can also become an inheritance for the generations of my own clan. My children, my grandchildren.
If we can bring that passion over to future generations and to hand that over to my children, and I hope that that same passion for conservation gets migrated over to my kids.
And what we've done together is create a sustainable source of funding that should outlive all of us.
You know, I think as far as B2 Gold is concerned, we couldn't have chosen a better target in which to put our efforts as far as the environmental and conservation pillar is concerned. And I want to stress there that the money that's going towards environment and conservation is actually going towards the people.
Rhino is for all of us, whether you are in Canada, whether you are in Vancouver, whether you are in the US. If you really want to see conservation at play with rural communities, I therefore humbly request each and everyone to join us on our Rhino tour and have a wonderful experience. This is what keeps rhinos on this planet.
I've done rhino trekking experience. It was just amazing walking in that landscape of the Kunene. And as we followed them, we could now find rhinos with the calf. We got the closest distance we could.
It's a warning sign.
And it was just amazing and lovely. It's something to experience that Namibia can offer. It's something that you have to do in your life.
Just believe